So in this video, I'm going to try to knock out the last two things that I wanted to cover for these topics, which are also taken from the book. There are two more proofs. One of them is pretty simple, which is just a proof of divergence of a sequence, which we've already kind of seen. I'm actually going to just be using basically the same. We're going to be looking at -1 to the end, but I want to just formalize it for you guys so you see exactly what it looks like. And then we're going to do a proof that involves an assumption of convergence that we have to exploit. Okay, so because that's very different from trying to prove that something converges. When you know something converges and you're trying to use that for something else, it's kind of like it can feel a little backwards, I guess. So let's start with the divergence. So, dang it. Prove the sequence an equals -1 to the n diverges, meaning it does not converge. Oh, wow. Diverges, meaning it doesn't converge to any number. Okay, so it's kind of flipped, right? I already kind of like covered what it looks like to state that a sequence does not converge to a specific number. In this case, we're trying to show it doesn't converge to any number. So what we can do is let A be any number. Okay, what we're going to do is let A be any number and then show. So sometimes it can be helpful to people like to write this. Want to show is what this stands for. And this kind of like helps you set a goal of what you're trying to do. Okay, so what we want to do is show that an does not converge to A, right? So we already let A be arbitrary, right? We have no control over A. So if we can show that an does not converge to A, regardless of what A is, that means that an does not converge to anything, okay? So I kind of got at this idea before. But now how to show that an does not converge to A regardless of what A is? Okay, well, the way the book does it is by contradiction, and I'll just go ahead and do that too. So suppose an actually does converge to A. Then what they do is they say, well, pick epsilon equal to 1/2, right? Then there exists a capital N such that for all little n bigger than capital N, an minus A is less than 1/2. Okay? Now, so the reason I can say this is because we're assuming that an converges to A. Obviously, that's not true, but that's the point, is that we're trying to derive a contradiction from that, right? Now, with the assumption that an converges to A, that means that because, the definition of convergence says for any epsilon, some n exists, that means we can pick an epsilon, whatever epsilon we want. We can pick an epsilon. And then by definition of convergence, there has to be a big N such that, for all little n bigger than that big N, this condition has to be satisfied, right? So I'm just sort of invoking the definition of convergence here, actually, right? So it feels different because we picked epsilon instead of letting it be something, right? But remember, we're not trying to show convergence. In this general context, we're trying to show divergence. But here, really, we're taking advantage of an assumption of convergence, basically, that we want to end up violating, okay? Now, so clearly, for some values of n bigger than big N, an equals 1, and for others, an equals -1, right? So we're just going to kind of do the same thing we've already sort of seen before, which is just kind of show the contradiction is that this function keeps jumping between 1 and -1, and there's no single number which is closer than distance 1/2 to both of these two numbers at the same time, right? So this means, since we're supposed to be guaranteed the fact that an minus a absolute value is less than 1/2, sometimes an is 1 and sometimes an is -1. So the distance between 1 and a has to be less than 1/2, and the distance between -1 and a has to be less than 1/2. So 1 minus a is less than 1/2, and -1 minus a is less than 1/2. So if you draw a picture of this, here's 0. Or sorry, yeah, actually, yeah. So here's 0, here's -1, and here's 1. Now, here's radius 1/2 around both of them, right? So the idea is that, oh yeah, we actually could have used epsilon equals 1 even. So I made epsilon smaller than it had to be, but whatever, right? These two conditions, so this one tells us that a is supposed to be in here, right? But this one tells us that a is in here. That's not possible. So if you want to do this, like make this argument formally, one thing you could do is use the triangle inequality. So say that, you know, let's see. So this is the same thing as, well, let's see, how do they phrase it? Sometimes this is a little bit tricky. I want to do the same thing they do. Right. So 2, which is this, 1 minus, so the distance between these two numbers is less than or equal to, right, of course, yeah. The sum of the distance from, so yeah, the sum of the distances from 1 to a third number and the other 1 to a third number. That's the triangle inequality. So, so what you could say is let's first write this as this equals 1 minus a plus a minus -1. Sure, why not? And then, so this is less than or equal to, by the triangle inequality, we can split this up. So 1 minus a plus a minus -1, right? And this is actually, these two things are equal to these. So, so in this case, if they were both less than 1/2, that would be saying that this sum is less than 1. But we just showed that it actually has to be at least 2, right? So that's the contradiction. So 2 is less than or equal to 1 minus a plus -1 minus a. Contradicting the idea that both of these two things are less than 1/2, right? Because they can't add up to be something less than 2, so that's bad. So anyway, so that's the proof of divergence. Let's move on to another slightly more advanced proof, which involves convergence as an assumption. And actually, if you noticed, since we were doing it by contradiction here, we actually did end up making a fake assumption that the sequence converged, right? So you actually just kind of saw what it means to be able to like use convergence as a hypothesis. But I want to show you in another slightly different setting, because I think sometimes it just feels different when you're not doing it by contradiction and when you're not dealing with such a concrete sequence. Because a lot of the time what happens is basically, like a lot of the statements that we're going to be making in this class that we want to prove will be something like, suppose a sequence converges, prove something about it, right? Or suppose a sequence converges and has some other properties, now prove something about it. And you don't know anything about what the sequence actually is. Like, you don't have a formula for it. You only have the information that it converges, and maybe it has some boundedness property, or maybe it's like increasing or decreasing, or who knows what, some other properties. But you don't have access to any kind of formula for the sequence. So you just have to learn to use these like general properties of sequences as building blocks in your proof, right? So let's do that in this case. So there's one in the book where they say, right, so, oops, suppose Sn converges to a number S, and Sn is not equal to 0 for any n, and S is not equal to 0. Show that the infimum, oops, of the set of absolute values of Sn, you know, well, yeah, I'll use their notation, over all of the terms in the sequence, the infimum of this set is greater than 0. So this is something you really should think about this carefully. And I'll return to this after we do the proof. I'll kind of help you think about it more by tinkering with some of the assumptions here and some of the statements, right? But this is where things start to get a little bit tricky because it can be counterintuitive sometimes, like why we have to make certain assumptions, what it really means for the infimum of this set to be strictly bigger than 0 is something you have to think carefully about it. Okay, I'll come back to this idea. But okay, so let's think about how we would prove this. Okay, so the idea is that there should not be, basically, this statement here, the infimum being greater than 0, essentially intuitively should translate, here, let me actually annotate this. So this there are not I guess how should I phrase this? There are not infinitely many terms Sn close to 0. Okay, so basically the terms of the sequence cannot get arbitrarily close to 0. Now, the question, so now if we're trying to prove that, you should ask yourself, well, why would that be the case based on the assumptions we have? Well, one of them is that, right, obviously none of the terms themselves are 0. So 0 should not be in this set, but that's not enough, right? Like even if these, even if they're all non-zero, you can still have a set of non-zero numbers whose infimum is 0, okay? And we'll come back to that idea. So it's not enough, but the fact is that they converge to something which is also not 0, okay? So the idea is that basically beyond a certain point in the sequence, all of the numbers have to be like super close to this number S, which is non-zero, right? So they can't be getting like arbitrarily close to 0 if they're stuck around S, right? That's the thing we're trying to exploit. And that's how we have to use convergence. So the book draws a picture, which I like. Let's say here's 0 and like here's S, right? So so let's say this is S over 2 and this is like 3S over 2. Actually, no. Let's just say we pick a radius epsilon that's sufficiently small, right? S plus epsilon. So all but finitely many Sn, right? All but finitely many of the Sn have to be within this bubble. If we, no matter what epsilon we pick, actually, this is true. So if we pick a small enough epsilon that gets this bubble not to include 0, right? If we keep it small and keep this away from 0, then only a finite number of the Sn will be anywhere outside of the bubble, right? And so basically all of these, their absolute values will be something, you know, bigger than, all their absolute values will be bigger than like S minus epsilon, for instance, right? So the worst thing we could have would be if some of the initial things, so like, you know, so in particular, for greater than capital N, right? For all n greater than capital N, Sn is inside this bubble, right? So, so this is for some capital N, right? So for some capital N, then all of the things after that are inside this bubble. So that means there are only a couple things. There's a handful of terms in the sequence early on, which might be outside this bubble. And some of them might get pretty close to zero, but there's only so close they can get because there's only capital N of them, right? So basically, so if you take epsilon equals, S over 2. This is the scenario where S is positive, but there's like a mirrored picture when S is negative, right? Where you just draw all of this stuff on the other side and do the same thing. So if you take epsilon to be absolute value of S over 2, that guarantees that this bubble, no matter what S is, this bubble will not include 0, right? So if we take epsilon to be absolute value of S over 2, so then there exists a capital N such that Sn minus S is less than epsilon for all n greater than capital N, right? That's that's using the definition of convergence, right? We're using it, we're exploiting the definition of convergence. We're not trying to prove convergence, we already know convergence. We're trying to exploit that definition, which is why we can choose epsilon in this case, right? We're not playing the game from before. We're choosing epsilon. So, and we're choosing it intelligently, right? So now we've chosen this epsilon. There has to exist, because of convergence, there has to exist this capital N, which makes this be true. So that means, so then take, the notation they use in the book is this. They define M to be the minimum of the absolute values of S1, S2, up to Sn, and then also S over 2, right? So what they're doing is basically they're saying, okay, in the first n terms, right, some of them might get pretty close to 0. They can't equal 0 because that's one of the assumptions up here. But here, let me switch to, yeah. So one of the assumptions up here guarantees that none of these will be 0, right? On the other, but some of them might be pretty small. They might get kind of close to 0 in some sense, right? But there's only finitely many of them, so we can just pick the smallest one. We can just pick the smallest one of these, and then also whatever this happens to be, right, which is right here. And no matter what, that will guarantee that every absolute value of Sn for any n, right? So let me switch back to this pen here. So now Sn, or actually, let me just even use a different index. K, I don't know, is greater than M for all K. Okay, for every index now, this little m is smaller than, well, okay, or greater than or equal to at least, right? And m is greater than 0. M is strictly greater than 0, which is important in this case, right? So what we've done is we've basically found, so the reason for this, to be clear, is that, if you take a random sk, either it's one of these first n of them, or it's after the index is, if k is bigger than n, then it's somewhere inside this bubble, right? Because of how we chose big N. But that means that the absolute value has to be at least S over 2, right? Based on how we chose epsilon, because it has to be inside this bubble. Okay, so that means all of the sk absolute values are bounded below by m. And we know the infimum of the SKs is greater than or equal to m, because the infimum is the greatest lower bound, right? So m we found to be a lower bound here, and the infimum has to be at least as big as that. And because m is strictly bigger than 0, the infimum is also strictly bigger than 0. So this took a bit more work than you might have guessed just from the statement, but this kind of argument you'll get used to, you'll get used to thinking about things this way if you just do enough of these. Yeah, it's hard at first, but it gets a lot easier. So I want to just finish off with a couple thoughts, okay? I'm gonna erase this. I'm gonna erase all of this stuff. So this is a good practice, by the way, for all of you. I very strongly recommend you to get in the habit of doing what I'm about to do, which is take any statement that you find that that we prove in the book or that you prove in homework or whatever, anything really that might be proved in any context. Take those statements and imagine what would happen if you messed around, if you tinkered with the different assumptions, right? So now let's imagine what happens, right? Okay, if we delete this assumption, for instance, then it becomes obvious, right, that the conclusion is not true anymore because now some of the Sn are actually allowed to equal 0, right? So 0 might actually show up in this set. So the infimum could actually equal 0. So that's kind of a fairly straightforward version. So, oops. So if we don't assume Sn equal, not equal to 0, then 0 can show up. Oops. So the conclusion is false. So show up in the set of absolute values. Right? Sorry for the handwriting. Can show up in this set, right? This set over here. So, okay. Now, what if we don't assume if we don't assume S is not equal to 0, then okay, so actually this would be, so I'll tell you, okay, the conclusion is false. A counterexample would be, and now just go ahead and pause the video and think about it. This is not a lecture question. You don't have to submit this on the homework, but just think about it for a bit. What would be an example of a sequence that satisfied all of these properties except for this one? And why is the conclusion no longer true? So if you did that, probably an obvious one you might come up with would just be Sn equals 1 over n, our favorite sequence that approaches 0, right? None of these are 0. Sn converges, but it converges to 0, right? Now, what is the infimum of the set of absolute values? Okay, sure, all of the Sn themselves are bigger than 0, but because they get arbitrarily close to 0, the infimum of this set actually ends up equaling 0. It's not strictly bigger than 0 anymore, right? So anyway, that's all for this lecture. So I'll see you guys in lecture 4.